Hey crew, this is my second attempt at this video, so the sarcasm is pretty high. I got all the way through it the other night and realized that the microphone was off and it didn't take. So I'm doing it again, and that's okay. So in this video we're going to talk about electrolytic cells. So the main thing here is that we're talking now about non-spontaneous cells. These are going to be your chemical reactions where your delta G is positive. All right, we know that's not helpful. If we calculate the voltage for these cells, for the reactions that we're given, these voltages are going to be negative. Again, both of those indicate non-spontaneous reactions. We can make these reactions happen. I didn't say these are impossible reactions. I said they're non-spontaneous. So what we have to do is overcome the lack of motivation, if you will, for these reactions. So let's start here with a brief recap, as you see on your screen here, of a voltaic cell. So let me just kind of back up a little bit. Voltaic cells are basically like what we learned in pre-AP as single replacement reactions, like I have up here in the corner. If I had aluminum plus copper 2 chloride, we actually did this reaction in pre-AP in one of our early clues of a chemical reaction lab. We had this big graduated cylinder of blue juice, and you guys wadded up a piece of aluminum foil and dropped it in there, and you saw a nice precipitation, or what you thought was a precipitation reaction, and really what you had was electrochem. Because what was happening was that the copper 2 ion specifically here, was taking electrons from the aluminum, which was donating them rather easily. And so the copper was reduced, and you saw that form in that graduated cylinder, if you can remember, that brownish precipitate, and then the aluminum went into solution, and that's why the solution lost its color, or got less blue, because I'm sure the copper was more in excess. But that's it. So why do we fool with voltaic cells if they're just single replacement reactions? Why can't I make a battery out of that ball of aluminum back in pre-AP? Well, when we just drop the aluminum into a beaker or whatever of copper 2 chloride, we can't control the reaction. It's totally spontaneous. It's all happening at once. It's happening all over the surface area, and it's basically over. All the stuff just goes poof, and it's done. There's nothing left. But in a voltaic cell, we separate the reactants, and we're forcing the reaction to occur by electrons traveling from an anode to a cathode. So it's almost like we're throttling the reaction back and allowing it to happen at a more controlled pace. So how does it happen? If it's spontaneous, how does it happen? Well, what you probably think of as this conductor, you probably see it as an empty pipe or something. And an electron gets released at the anode, and it's shot down the pipe like a cannonball out of a cannon, and it just rolls over here. That's not really what's happening. This conductor wire is a piece of metal. So it's got metallic bonding all the way through it. And so it's a little still simplification, but it's a little bit more accurate. Think of just a non-stop line like at Disney World or Six Flags of electrons all up and down this wire. So at either end, attached to the metal, you've got an electron on the brink, standing on the edge of a cliff, and one of them is going to get pulled off. Which one? Well, it's the one that's getting pulled harder. And the one that's getting pulled harder is going to be drawn in by the most electronegative element. In other words, the one with the largest reduction potential, the cathode. So what's going to happen is the cathode's just going to pull that electron off. And I guess more accurately, it would be let's just say this is copper or something. And let's say this is copper plus 2. So it's really more accurately, it's getting pulled in, conducted down into the ion. But anyway, it gets pulled here off. And so what that does is it pushes all these other electrons, just sort of like ping pong balls in a roll, just sort of slide down to the next one. And that creates a vacancy right here. And that vacancy is going to be filled by an electron coming out of the electrode. And that is going to have to come from somewhere else. So we're pulling electrical charge through the ions into the anode, which in turn just sort of scoots another electron into line around here. So that's a voltaic cell. And it happens on its own because these two, whatever they are, these two reactants want to react by themselves according to the activity series. But if we go to a different situation where it's non-spontaneous, the reaction doesn't want to happen. So in this example, we have molten sodium iodide. So that just means an ionic compound and it's been melted. It's like, think of kind of a lava type substance here, sort of like a, real thick liquid. And if it's melted, even though this is sodium iodide, you can sort of think of this now as two oxidation states here, sodium positive, iodide, which is negative. And the reaction that we're proposing here is to plate out, solidify, reduce, if you will, sodium here at the cathode, and we want to oxidize iodide to iodine at the anode. Well, if I just hook these two up like we did in the voltaic cell, nothing's going to happen. Both of these substances are perfectly fine being sodium positive and iodide. There's no need. So nothing's drawing the electrons off the edge, if you will. So what we've got to do is intervene. And that's where this power source comes in. This is just a battery. It could be a wall plug-in, but the same thing applies, that in a battery or any other voltage source, you're going to have an anode and you're going to have a cathode. So in essence, for an electrolytic cell, we run another kind of either a chemical reaction if it's a battery, or it could be just plug-in physics, just providing a voltage difference. Let's just pretend, for the sake of this, that this is a battery. So we have a parallel chemical reaction going on here. So because this cathode is not powerful enough or willing enough to draw electrons in, we're going to force it. We're going to shoot them at them. If this were a 9-volt battery, even for this one, I did the numbers earlier, then plugging this up would force electrons through the sheer numbers here to be pushed down toward this cathode. So we will get reduction of sodium at this cathode if we hook it up to an external power source. Okay, so now that works, but inside the power source, if we're losing electrons, we're quickly going to build up positive charge over here. So we have to hook this positive terminal of the parallel source here into the anode of our chemical reaction, so that we can make oxidation happen here and sort of replenish the supply of our electrons that we're kicking out into our cathode from the anode. So we've completed the circuit here. You'll notice some things are missing. We don't have a salt bridge because these ions can just flow anywhere they want. The unwanted fast reaction doesn't happen like it would in a single replacement, like a voltaic cell reaction. So we don't have to worry about that. So if we have molten ionic compounds and I want to turn them into the elements, this is what early chemists did. They liquefied and then used electrolysis here. This is what this is called, electrolysis, to pump electricity into these molten substances, and we got the elements out. This is how sodium was first produced in the UK back in the late 1800s, early 1900s. No, it was early 1800s, late 1700s. I forget the exact date, but this is how it was done. Now, we don't do that a lot. I'm sure you haven't seen me walk around pumping electricity into molten ionic compounds because it has to be pretty hot. And we typically don't have that capability. So let me toggle back over for a second to the PowerPoint. Give me just 1 second to pull that up. And it's going to be a pain. We would expect nothing else. So back to this. So when we do this electrolysis reaction in an aqueous solution, we got problems. We got things we need to work out. So what's going to happen is we're going to have competing reactions at the anode and the cathode. It's not going to be so simple as just making sure Let's try this one more time. I really want to get my PowerPoint going here. Well, I hate it took so long, but sometimes it's just a pain. You just got to work through it. So we're back. We got it going here. So as I was saying, in an electrolytic cell where we have aqueous reactants, so in this case, we would have like, I'm not going to go back to the picture yet, but we would have the sodium in aqueous form instead of liquefied form. And then maybe the chloride or the iodide also in aqueous form. So there's water there. So we got competing reactions. We know that at the cathode, we want to reduce the metal ion. Okay, we know what that's going to take. We can look it up in the back in the appendix and see what the reduction potential is. But if it's too negative, then we run the risk of the water reduction to make hydrogen gas be more favorable than that metal reduction. So as you can see on the screen, the cell potential, or the reduction potential for the water is negative 0.83 volts. So any metal cation that has a reduction potential less than negative 0.83, you will not be able to plate that metal out in an aqueous electrolysis cell because you'll be making hydrogen instead of the metal you want. So you've got to be at least negative 0.83 volts or higher or more positive to make it work. All right, likewise at the anode, the competing reaction is the oxidation of water to make oxygen gas. And so usually we have two competing reactions. If you look in your appendix at the half reactions, you'll see two for for oxygen. One is the oxidation of H2O to O2, and that has a positive 1.23 volts. Or you have the hydroxides that we all know that are in water and at equilibrium from our acid-base unit. That hydroxide can be oxidized to O2, and we can see that's a 0.4 volts. Now, when we look at the anode here, we're not looking at the most positive to see what's favored. We're looking at the most negative. So most of the time, that hydroxide reaction is the most favorable. And under regular conditions, that means that anything we want to oxidize at the anode has to be less than or more negative than 0.4 volts. There's ways around it that I'm going to show you in our one example here for this. So what I've got here is silver fluoride aqueous, and I want to make solid silver and gaseous fluorine from it. So let's go through this reaction and see if I can get this proposed reaction. Silver reduced, fluoride oxidized. And this is aqueous. So here's what could happen at the cathode. I could run my silver reduction, no problem. Or the water can be reduced to H2. So let's look at the reduction potentials for each of those. Silver is 0.799. The water is negative 0.83. For the cathode, we want the most positive. The most positive will happen. And in this case, that will be the silver. So yay, I can make my silver at the cathode here, just like I want. Let's check out the anode. So here are the possible reactions at the anode. I can oxidize my fluoride to fluorine, like I want, or I could oxidize water to O2. So now maybe you're thinking, well, where's that hydroxide thing I just showed you? Let's go look at the problem statement again. We did this in an acidic solution. So this is a very common thing to do to keep that hydroxide reaction from happening so easily. We just acidify the solution a little bit, and that essentially neutralizes all the hydroxide in the solution. So really you don't have any hydroxide left. And that means this water reaction, which is harder to do, is the only option you have. Okay. Well, let's check out the cell potential, the reduction potentials. Fluoride to fluorine is positive 2.87. Water to oxygen is 1.23. Now remember, this is the anode. I don't want the most positive, that's the cathode. For the anode, I want the most negative. So in this case, the most negative number here is positive 1.23. So that tells me I will not be able to do the oxidation of fluoride at this anode. So water is going to be preferred, and if I were to actually set this cell up, I'm going to see bubbles forming at my anode, and if you're not prepared for that, it could be an explosive situation. So here's what's going to be the overall reaction. I have my silver, and then I have the water reaction. Then I have to go back and balance these two half reactions. It takes 4 moles of electrons, so you can see what we get down there. It's not what I wanted, and that's the voltage. And the negative 0.43 volts, of course, is non-spontaneous. Water doesn't just decompose like that. So that tells us that's at least the amount of voltage I have to pump in from the external source to make this reaction go. AA battery would do it. I think a AA battery gives 1.1 volt or something like that. So that's all the power you would need to get this one started. Alright, let's see if we can toggle back to what I was working on before. Alright, so here I have this thing. How do we make it spontaneous? Remember that we are supplying electrons from this source right here. There's chemistry going on in this battery. Electrons are being generated at this anode, and we are forcing electrons down into this cathode. And really nothing changes in the way we set this cell up. What used to be the cathode is still the cathode. It's just that we have to bring electrons in from the outside source because this anode doesn't have the punch to send electrons over. Alright, so electrons go to the cathode, which means that the anode of our chemical reaction has to supply electrons to the battery to replace what it uses. That's an electrolytic cell. They're not that complicated. You just kind of have to keep the potential water reactions from an aqueous electrolytic cell in mind. And then otherwise, you just got to kind of turn the way you think about it. This is non-spontaneous, negative voltages, positive delta G's, everything else works the same. If you have any questions, let me know. I'd be happy to go through it with you again.